Hello everyone, my name is Jeff Gagnon. I work with the Arizona Game and Fish Department. I'll be presenting with Tim Hazlehurst of Crosstech LLC on the implementation and accuracy of thermal and radar technology. The focus of my presentation will be on the thermal side of things, and then I'll pass it off to Tim for the radar side of things and some additional information on both types of systems. Thermal radiation, that bottom wavelength you see there, is not visible to the human eye. So it requires a special sensor to see the difference in temperature compared to its background. Here's an example of some people walking through a set of thermal sensors to determine whether or not they have a fever, and you can see the one person there has a high enough temperature to determine that they have a fever, and it's about a 1 degree difference. Thermal can actually see differences down to 0.01 degrees Celsius, so it's pretty accurate. Thermal sensors, like I said, detect differences in temperatures compared to their surroundings. In order to be able to use them as animal detection, you have to use a complex integrated analytical software that evaluates some additional components, including the size of the animal, speed, direction of travel, etc. An example of this type of system is the Arizona State Route 260 elk crosswalk near Payson, Arizona. This project was focused on elk because elk was a safety concern. As you can see, if you hit an elk, it's a pretty major event. Preacher Canyon project was completed in 2000 and included 2 underpasses to allow elk to cross under the road to this riparian meadow. With that, there was only a small section of fence, that yellow you see there. So the elk vehicle collision rates outside of that area continued. So from 2001 to 2006, we saw about 12 elk vehicle collisions per year in that area that I just showed you. In order to address the elk vehicle collisions in that area, we were able to use GPS collared elk. We were able to use this data to use a data-driven approach to fence the area where the animals were crossing and the collisions were happening. What do you do at the end of the fence? Here is an example of signs. And usually, signs don't work themselves. Here's an example of kind of like that cartoon of 4 watch for elk signs within a quarter mile. And what happened here, we had a minivan hit 7 elk at one time and walk away from that. There's one of those signs right there. So as you can see here, the animals walk along the end of the fence, they round the corner, they hit the detection zone. They're detected by these thermal infrared sensors, which you see here. I'll talk more about that. And then these signs come on to warn the motorists. One other component I wanted to mention here is this electrified concrete or Zapcrete, which we put in here in order to keep animals from going inside the right-of-way fence. There's an example of our 2007 system used a target acquisition software that was thermal based. Year 2, year 5, and year 9 is when we did our evaluation, and we saw about a 7 mile per hour reduction in speed. So looking at motorist alertness, we look at the portion of vehicles braking. And our sample size there was about 19,000 vehicles. And what we saw was about 11% of the vehicles would brake with the signs off versus 67% roughly with the signs on. So the odds of braking with signs on versus off was 17 to 1. If you wanted for more information, you can see the paper that was included with this presentation, where you can reach out to me. We saw accidents reduced with elk by 97%. So we had a pretty successful setup there with a combination of the fencing that actually did a lot of the heavy lifting and the crosswalk, where we were able to warn motorists that animals were crossing there. So the 2018 upgrade of the system began with Arizona Department of Transportation, Arizona Game and Fish Department, and Crosstech working together on this. The upgrade included system components upgrade that used FLIR cameras, which was more replicable and more easily replaced, because ADOT does use that type of sensor for their wrong-way driver warning systems and other systems that they work with. We wanted to look at the evaluation of the reliability with a goal of 95% detection of large animals, quote unquote, and less than 10% false positives. And once the desired reliability was achieved, ADOT personnel trained on operation and maintenance, and then they would take over the system. So where did we get those accuracy numbers from? They came from some evaluation metrics from a previous study on animal detection systems that stakeholders agreed that animal detection systems should detect 91 to 95% of all large animals, quote unquote, and that animal detection systems that had a false detection rate of 6 to 10% or less would be acceptable. and use of animal detection systems should result in a reduction of 71 to 80% or more in wildlife collisions. So we had the accidents nailed down. Now we're looking at the new system, making sure the accuracy is there. So what do we consider as a large animal? We used anything larger than a fox as our cutoff. And so animals to the right of that green bar should be detected. Animals to the left should not be detected. So how well did the system work? So we had 752 animals during our evaluation. Most of them were under the size filter. As you get within the size filter, the smaller animals like the fox size, bobcat, the accuracy was marginal on those. As it got a little bit bigger to coyotes, we got most of the coyotes, but then as you get a lot bigger, you get to 100% accuracy for elk. And so as the animal gets larger, the accuracy increases, which actually works pretty well from a human safety perspective. But here's an example of the detection system. The white box is the detection area. And when it's white, it's lit up. It means that the signs would be on. For our tests, we did not have the signs come on because we wanted to make sure the system was accurate before we turned the signs on. So this white box here is when an animal has been detected and determined that it is an actual target. Then that white box will come on, and that in turn turns this larger box on. So you see the trues and falses. That's the criteria. So you've got your size, your difference in temperature, and all the criteria that determine whether or not that is a target. And so I'll show you here. So this one's already been detected as an animal. It goes for 2 minutes. Watch these animals come in from the road here, and you'll see a black box. And when all the trues hit, when you see all 5 T's, then that white box come on, and you see this with this calf too. That means the system will be on for another 2 minutes every time you see all those T's come on. It would continue to keep the signs going. Here's an example of a non-target. So you can see here comes this calf. It's a target. All the T's are there. But look at this cottontail rabbit right here. It's hopping around, and it's not getting all the T's. And the size filter especially never actually picks it up. Here's another animal coming in. All the boxes on. You see that rabbit left. No issues there with picking it up. So here's an example of why those sometimes get triggered. This is a house cat, and you can see that it's coming towards us. The size criteria. Look here. Here's some weeds that are blowing around over here that the system's not saying is a target. But once this F changes to T, it means it's large enough. As it gets closer and closer to the sensor, now all of a sudden, nope, it turned the signs on. So you can kind of see how it can kind of trick the system a little bit. So as far as false positives, we had 82 false positives. The signs would have been activated for 2 minutes each, or 164 minutes out of the 129,600 minutes that we evaluated. And so that was well under the 10% false positive rate. The FLIR sensors identified that 6 of those false positives actually had animals. We called them false positives because they were under the size filter. The remaining were related to vegetation, and so we discussed options to reduce the vegetation to increase the accuracy of that system. So the system's ready to go live and hand off to ADOT, and we're still working on that. So why is a detection system even needed? So we did not have the signs coming on here because we were still testing the system to make sure that everything was accurate before we turned the signs on. So this is an example of if you just had, the signs would be on, as you can tell by the box, but if you just had a crossing with no warning system, you could see that an animal can get hit, like this calf right here, and how it got hit, but it's not dead yet. Now it is. And so, you know, that's basically what happens if you're not alerting motorists of what's there. Now here's an example. If that same car had swerved instead of hit these animals, then it might have swerved into that semi, and we would have potentially had a motorist fatality instead of an animal vehicle collision. So the warnings all the way around are good and can keep things safe. Moving to New Mexico, Cuba US 550 system, there's a detection system there on either end of the fences that guide animals to 2 underpasses. And so here's our motorist response system at Cuba. It not only includes the brake light cameras like you see here, but it also includes software to evaluate driver speed. So now we don't have to hide in the bushes anymore when we do this. We actually can do it even from another state. You see this vehicle coming down here. You can watch brake lights if the signs were on. It's going to turn into the detection system, and you'll see these signs come on. So there's a lot of things we can evaluate with the system to determine, you know, motorist behavior and accuracy of the system. So I'm going to go ahead and pass this on to Tim to do the radar side of things.
Thank you, Jeff, and thank you all for attending. I'm going to go through the keys to successful implementation of a wildlife detection system and the use of radar in wildlife detection systems. This picture actually in front of us here is a pretty good representation of a good working system. You have the car coming towards us and some deer down here on the left side at the bottom of a bank, which may or may not be visible to the car. But this radar has picked up the deer, and on the back side of this pole, there's a sign flashing just like this one here saying slow down. And this camera here on this pole is looking down at the area underneath this radar, which happens to be a blind spot for the radar. So a good example of an integrated system using multiple sensors. There's a lot to go through. I'll go through it quickly. Hope that maybe we can expand on this in the question and answer period later on. A little bit about us. Since 1986, we've been designing, manufacturing, and distributing a new generation of electric fence energizers. These are the same energizers that we now use in electrified barriers in the roadway. Our first experience with wildlife detection and motorist warning systems began about 12 years ago. Our passion now is inventing, designing, installing, and maintaining wildlife detection warning systems and electrified barriers. I'd like to shout out to our teammates, PBX Engineering up in BC. They have 24 years of engineering experience in multiple disciplines that are needed for this type of application. And we're the principal designer of the successful BC radar system we will discuss later. We've looked at systems of the past to help inform good implementation of systems currently. Many of the systems in the past have experienced a lot of false positives where there are no animals present, but the warning signs are flashing, and then the opposite of false negatives where animals are actually present and the warning signs were not turning on. We've seen poor design integration, wrong sensors for the application, and ultimately too much maintenance to keep the system working. The sensor type is very important, even though it's not the only component. Brake beams or light curtains only really provide one point of reference, which is not enough to really track animals around the roadway. Geophones using vibration in the ground are tough to calibrate in the roadway environment. Wrong types of radar, motion sensors without enough sophisticated filtering, thermal cameras with low resolution or poor analytics. All of these have been a problem and have resulted, unfortunately, in loss of motorist confidence in a system, leading to complaints and reduction of motorist response, and ultimately systems being discontinued. So why is implementing wildlife detection systems been so difficult when the concept of operation is really fairly simple? We're detecting wildlife, we're activating advisory signs. They stay active while the wildlife are within the detection zone. And then when the wildlife clears the detection zone, the wildlife system deactivates the advisory signs. Some of the reasons we think are essentially underestimating the complexity of the implementation. Seeking the perfect sensor as a standalone solution rather than looking to integrate multiple sensor types, and not using a methodical systems design approach, including robust validation. So the things that need to be considered before you even begin designing a system include wildlife behavior, such as are they herds, are they individuals, are they lingering, are they moving across the road with a mission, are they fast, topography, lines of sight, is vegetation going to be managed, will we be able to use fencing to limit the length of roadway we need to cover. And then most of the time we're in really tough weather conditions, which are hard on all types of electronics. Have to consider access to power. Will it be solar versus AC? Motorist conditions, motorist attitudes, speeds, local versus new motorists, signing strategies, and then stakeholder expectations. Have to cover maintenance requirements, warranty, system life. Is it going to be temporary or permanent situation? Etc. As we've seen, the operating concept is rather simple, but there are many challenges and considerations, ultimately resulting in a very complex system with hundreds of components required. It's important to choose the components to meet robust design parameters and realize that there's no substitute for real-world experience with components. Components with the same specs often don't operate the same in the environment. Multiple sensor type integration is often needed, and it's extremely important, thorough validation and testing before commissioning. The nature of systems, of course, is that they are only as functional and reliable as the weakest component. On the right is an example of a simple pole which required 4 modifications, structural modifications to withstand 90-mile-an-hour gusts, which otherwise made the thermal camera on top completely inoperable. So in order to address this level of complexity, you really need to pick your team carefully and make sure that you have all the expertise areas that you need around the table. These would include electronics design, power supply design, surveillance system engineering, communications design, software and logic design, ITS integrations, wildlife behavior, mechanical and civil engineering, and of course, a contractor that will do a good quality installation. Changing subjects now to talk a little bit about how radar works. Radars emit a beam of energy in the form of a radio wave, which then strikes an object, in this case, our wildlife. The energy that's returned from the object or wildlife provides us with the ability to, quote, see the object. We can further determine the behavior of the object in terms of travel direction, speed, and location from calculations on the waves that are returned and compared to the radio waves that are emitted. The electromagnetic spectrum for radar is somewhere between radio waves and infrared waves that Jeff was talking about for thermal imaging. It's a little closer to the microwave section of the electromagnetic spectrum. To better understand how radar determines the direction and speed of wildlife, we can compare radar waves to sound waves that we can hear. For example, when we're listening to a siren coming towards us, we hear a higher frequency sound or a higher pitch sound here over on the right. And when the siren is moving away from us, we hear a lower frequency sound, which sounds lower in pitch. In a similar way, the radar takes the reflected waves and measures the frequency of the wavelengths to calculate both speed and direction of travel. This is an example of a complete radar system layout in British Columbia. You can see on the right here, the gateway sign. The shape of the road follows my arrow here. There's a big bend in the road here, and then the last gateway sign. There are 3 signs in each direction, and you can see the complexity here in integration when you look at how many pieces of equipment are in each pole. On this pole, for example, right here, we have a radar, a point tilt zoom camera, a thermal camera, and then communications antennas to the signs, to activate the signs. You have the same thing on this pole over here and on this pole over here to completely cover the area. It's important that you have a robust control system for validation. On the left here, we see the 2 red dots. These 2 red dots are objects that the radar has picked up, believing that these are wildlife. And indeed, we're able to validate that on the same time base by looking at the thermal camera image, where you see on the left side of the road here, one animal has just crossed the road and one is entering the road right here coming out of the forest. The performance and results of the thermal radar system proved to be 96% accurate in terms of recognizing wildlife and turning on signs. The wildlife vehicle reduction in the 2 corridors there was 79% and 23% respectively the first year, 58% and 38% respectively the second year. There's a difference in length of the corridors, and yet there was not a difference in the number of signs used. And possibly this contributes to the difference in wildlife vehicle reduction in the 2 corridors. So definitely more research is needed to convert the proven 96% accuracy of the radar system to detect wildlife and activate signs to a higher reduction result in wildlife vehicle collisions. Possible areas of research, again, types of advisory signs and effectiveness, numbers of signs, and public education around what the system is doing. In addition to the benefit of using wildlife detection systems to mitigate collision where other methods are simply not an option, wildlife detection systems can be significantly less expensive. Without time to go into detail now, if you look on the top row, you can see that a 1 mile stretch of wildlife detection system is often 1/2 the cost of fence and fence end treatments. Here we see $600,000 for 1 mile of WDS, 1.4 million for a fence corridor with 2 underpasses. If you increase the distance, the cost can be 1/3 or even less than other types of infrastructure construction with fence, underpasses, or overpasses. An interesting thing you can do with the wildlife detection system is put it on a mobile platform where you can move it around and have a fast response to a dangerous hotspot, or you can move the system if the migration area from the original location happened to shift, or if you have 2 migration areas that are occurring at different times of the year, you could use one system to cover both. You can also do research, do behavior analysis with the data around the roadway and move it from place to place. So in summary, both thermal and radar sensors share a vital role in successful wildlife detection system implementation. Each sensor needs to be carefully matched to the unique requirements of the wildlife crossing area, and often integration of more than one sensor type is needed. With good implementation, WDS using available technology can be very effective from cost, reliability, WVC reduction, effectiveness, and low maintenance point of view. The thorough systematic approach, employing full range of appropriate expertise to implement a wildlife detection system from start to finish, is a major key to success in reducing wildlife vehicle collisions. So at this point, I'd like to end the presentation and thank you and look forward to your questions.